Welcome to AP Calculus BC video for skill number 249. I can use substitution to evaluate integrals. And the trivia question for the day is, we all know that these parts of the wheel are called spokes, or most of us know. But the trivia question is, a spoke is used to connect what part of the bicycle to what part of the bicycle? Or more specifically, what part of the bicycle wheel to what part of the bicycle wheel? What is the name of this and this? Alright, in this video we're going to learn to evaluate integrals that are going to require substitution. And oftentimes what we'll get is an integral which looks like we can't find any direct antiderivative of it, and perhaps substitution is one way that we can solve it. And the integral here, oftentimes what you'll find is if you have like the product of two different functions, that might be a way to recognize substitution. Another way you might recognize substitution is one of the terms is a degree higher than another term. All in all, there is no direct path to recognize substitution problems, but the more we do them, the more familiar we get with them. And in order to do substitution, this is kind of like if you had the chain rule of a function and you were integrating something that had been chain ruled. So trying to get back to the original composite function. In this one observant student might notice that 8x dx is a multiple of the derivative of 5 plus 2x squared. The derivative of 5 plus 2x squared is 4x dx, and we'll notice that 4x dx is very closely related to 8x dx. So if we let 5 plus 2x squared be our u value, then the derivative of u with respect to x is 4x dx. Or if you wanted to, you could say du dx equals 4x, and then from there you can write du equals 4x dx. If we double that, we get 2 times du, which matches more like what we have here, the 8x dx. And so now what we can do is we can substitute the values in. So we're taking the square root of u, which remember was 5 plus 2x squared, and then our 8x dx gets replaced with 2 du. And from that we can pull the 2 into the front, and what we have is u to the 1/2 du. And this is something that we can find the antiderivative of because it's just a power rule for integration. So we add 1 to the half and we get u to the 1.5 all over 1.5 plus c, because it's an indefinite integral. Then we resubstitute 5 plus 2x squared back in for our u, and 2 over 1.5 is 4/3. Let's do that in a different color. Let's do it in black. 2 over 1.5 is 4/3. And then we have u to the 1.5. So that's the method that we use for substitution. Like I said, one good strategy is to recognize functions that are 1 degree off in power, like 2x squared to 8x, or maybe we might have trig functions where we recognize that 1 power off. Not 1 power off with trig functions, but the relationship between sine and cosine when we're doing the derivatives. Let's actually take a look at some examples down here. This first example, we only have one function, and so we're going to substitute the inside as our u. So we're going to let u be 3x plus 2, which means du is, the derivative of that is 3 dx. So what we now have is the integral of sine of u, and then our dx, or you could say du over 3 equals dx. Our dx is replaced by du over 3. Using properties of integration, I can pull the 1/3 out to the front and get sine u du. And the integral of sine is negative cosine. So what we have is negative cosine u over 3 plus c. And then we substitute in our u value to finish it all out. So if we substitute in our u, we get 3x plus 2. This is all over 3 plus c. Alright, the next example, what we have is sine x times e to the cosine x, and sometimes it's useful to take our exponents, especially in e raised to something, take that and let that be our u. Another thing I noticed is cosine and sine, those are very closely related when you're talking about derivatives and integrals. So I'm going to let my u be equal to cosine x. Oops. Let u equal that. So if u is that, then the derivative of u is equal to negative sine x dx. So we can substitute these in. The sine x dx gets replaced with negative 1 du, and then e to the cosine gets replaced with e to the u. If we apply our properties of integrals, we can pull the negative out front, e to the u du, and the integral of e to the u is equal to e to the u plus c, and then we have to substitute in our u value to get our final answer, negative e to the cosine x plus c. And there's our final answer for our indefinite integral. Alright, let's look at some definite integrals here. And the approach with definite integrals is not very different. So what we are going to do is we're first going to find our u value. So in this case I'm going to let u be 4 minus x squared, which makes my du negative 2x dx. Or I could think du over negative 2 will replace x dx. So that x dx gets replaced with du over negative 2. And then the square root of 4 minus x squared gets replaced with u to the 1/2. And then the tricky part is we have two approaches, and I'm going to show in each example a different approach. This approach would be to replace the values of our limits. So if u is 4 minus x squared and we stick 0 into that, what we're going to get is 4 minus 0 squared, which is 4. So we have a new limit of 4. And our upper bound, we stick 2 into the function, and we get 4 minus 2 squared is 0. So our new upper bound is 0. And if we apply properties of integrals, we have negative 1/2 integral 4 to the 0 of u to the 0.5 du. And this is equal to negative 1/2 u to the 1.5 over 1.5. Because we've replaced our boundaries, we don't have to substitute back in. We can actually evaluate this function. So if we evaluate, what is this, negative u to the 1.5 over 3 on the boundary 4 to 0. So we stick 0 into the function, and that's our upper boundary, and we get 0, and then we stick 4 into the function, and with 4 in the function we get negative 8 thirds, and so this is all equal to a total of 8 thirds. So in the end, I just want to repeat that I changed the boundaries of our integral because I did not substitute back at the end. I could have, if I wanted to, at this point, substituted 4 minus x squared in for u and then use the boundaries 0 to 2. And I'm going to use that approach on the next problem. So let's take a look at the next problem. What we have here is a problem which looks a little bit tricky, but we might realize that with a little manipulation we can reduce the problem to something that's a little bit easier. Let's first split it into two fractions. So I have 1/2 d theta minus negative cosine 2 theta over 2 d theta. And that allows us to factor out the 1/2, and we're taking the integral pi over 2 of d theta. We're going to pull out the negative 1/2 and get the integral of pi over 2 of cosine 2 theta d theta. And we're going to need to use substitution for this integral, but not this integral. So I'm going to do a u substitution of, we'll let u equal 2 theta, which means du equals 2 d theta. Or if you wanted to, du over 2 equals d theta. So that allows us to replace the integral 0 to the pi over 2 cosine of u, and then du over 2 for the d theta, which gives us 1/4, because I'm pulling the 1/2 to the front, of cosine of u. And the integral, in truth, since I'm writing it in terms of u, I should replace those values. I just have to keep in mind that in the end I'm going to substitute back. So the integral, or the antiderivative of cosine, is sine. So I have 1/4 times sine of 2 theta evaluated at 0 to pi over 2. Also, we want to take this one down, so we have 1/2 times theta evaluated at 0 pi over 2. That gives 1/2 times quantity pi over 2 minus 0. So this piece is pi over 4, plus, we need to evaluate this piece, and this all equals pi fourths plus 1/4 times, it appears to be 0 minus 0. So this all cancels, and we get a final answer of pi over 4. So this example, I did not substitute in the boundaries, so technically this is improperly written. I should have replaced those boundaries, but I knew that in the end I was going to substitute back. So I prefer substituting the boundaries in, but you're welcome to use whichever approach feels more natural to you. So let's take a look at the last page. Alright, so recalling the chain rule, the derivative of the chain rule states that if you have f of g of x, what we do is we take the derivative of the outside and we multiply that by the derivative of the inside. So as you can see, this here looks a lot like what we have here. And the substitution is basically saying that this is our du and this g of x is our u. So what we're finding is we have f prime of u du, and the integral of f prime of u is f of u. And if we had said that u was g of x, then f of u is equal to f of g of x plus c. So we can see how the chain rule is now related to substitution, and that may be of benefit to AP testers. I provided at the end of the notes 3 problems that I pulled from AP tests as an extended challenge to you. I think that the first 2 problems are kind of straightforward, evaluate the definite integral. The last problem, I think, is a really creative way to test whether or not you understand how substitution works. So this was also pulled from an AP test question, but it does not definitively look like substitution until you think about it in those terms. So good luck with those challenges, and thanks for watching. Thanks for watching. I hope you enjoyed this one and you challenge yourself with those AP questions in your notes. The answer to the trivia question is the spoke is used to connect the hub of the wheel to the rim of the wheel.